Okay, so now we're going to transition from regression to classification. So despite the name logistic regression is often used for classification, and I'm going to explain why. So I'm going to start now with a brief introduction to classification and some problems in classification, namely linear separability, and then the problem of using something linear to separate classes that cannot be linearly separable, but using the same trick of going to higher dimensions with a nonlinear transformation. So let's start with this notion of separability. Suppose that we have these data points. So in this case, our data is two-dimensional. We are not trying to predict this y value. We have two values for x, for the features vector. And we have two classes, this blue one and the red one, which actually this is normal cells, these are tumor cells, and these are the activities of two different genes. And we want to find a way of deciding from the activity of the gene if a cell corresponds to a tumor or to a normal cell. So we want to find some frontier here between these two classes, learn the frontier from these points, and then use that to predict the class of some cell in the future from the gene activity. So this is a classification problem because we are not trying to predict a continuous value, but we're trying to predict a class, and we're trying to classify our points into different groups. This frontier here, this linear frontier, since we are using a linear function to discriminate between the two groups, it's called the linear discriminant. And we can use the linear discriminant to separate two classes if they are linearly separable. If we cannot do this, then the classes are not linearly separable. For example, if we plot the same thing but with two different genes, then there is this frontier between the two classes that we cannot completely separate in our training set using a straight line. So these are not linearly separable. So in regression, we saw that we defined a straight line. The first example we saw last week, we defined a straight line with these parameters, these two theta parameters, and we used that to try to approximate our model. In classification, we don't need only the line. We actually need to know which side of the line each of our class is. So we are assuming we are dealing always with two classes. This is binary classification. And we need to know both where the frontier is and where the positive class is and the negative class is. So in this case, what we're going to do more generally, we can imagine that we have a hyperplane in n dimensions, and we want to specify that plane by using a vector that is pointing to one side of the plane. That will be the positive side, the other side will be negative. So basically our separating hyperplane will be this vector of coefficients w multiplied by the vector of input values. This input vector x can be of any dimension. In this case, if we are using two genes as the input, it's two-dimensional. If we use 10 values, then it has dimension 10. And then we also have a constant, because this gives us the orientation of the plane, and this constant value tells us where the plane is relative to the origin. So in our case, since we are using, if we are, for example, using 3 dimensions for our separating plane, we would have something like this. Suppose that we have a three-dimensional problem. We wanted to split the two classes with a plane, and we have this vector that indicates where the positive class is. And the plane corresponds to this equation where points multiplied by the vector and added this extra coefficient give 0. So that expression here is positive on this side of the plane, negative on the other side, and 0 exactly on the plane, because these would be those perpendicular to the vector we are using. So this is basically how we can define a linear discriminant in n dimensions, by defining a vector perpendicular to a plane plus this other coefficient w0 that tells us where the plane will be relative to the origin. Now what we need to do here, so we're going to have a frontier determined by this function, This function will be positive on one side of the frontier, negative on the other side. This is what we want for the classification problem. So everything here is a positive class, on the other side is a negative class. But now we need to find out where to put the frontier. So this is the question, how we're going to find the discriminant. And what I'm going to do now is to start giving you the wrong answer. So we want to find the discriminant, and this is how we should not find the discriminant, because it's going to give the wrong result. But why it gives us the wrong result is informative and allows us to understand a bit the difference between regression and classification. So to do it the wrong way, we could try to do the same thing as we did with regression. We're going to minimize the quadratic error. So when we were fitting our polynomials, we were minimizing the distance between the errors, the points and the line that we're trying to fit. So we use the square of that distance, minimize everything, and our line tried to pass through all the points. So let's try to do the same thing, but in this case we know that there is one class that is positive, the other class is negative. Our function is negative on one side, positive on the other, so we can try to do something like this. We're going to do the difference between what our function is giving us and the value of the class of each point. So we're going to try to put our line in a way that the positive classes will be on the positive side and the negative classes will be on the negative side. And we're going to do that by minimizing the quadratic error. So we're going to use these data on gene expression. We're going to use these two genes, carbonic anhydrase 4 and this cyclase activator, and there are two classes for our data. So these two columns give us the activity of the two genes. These are the input values, the X values, and this is what we're trying to predict, which is the class, whether the cell is a tumor cell or a normal cell. So we are going to use this training set to try to fit the best, to find the best discriminant. Now we're going to rescale our data, because the gene activities may have different scales and so forth, and we saw in the previous lecture just a simple way of rescaling, simply divided by the maximum. But there are actually two more sophisticated ways we can do rescaling. One is called normalization, which is to bring everything to an interval between 0 and 1. So to do that, we subtract from each point the minimum, from each value, the minimum of that value on all our points, and then we divide by the difference between the maximum and the minimum. So everything will be shifted and rescaled to a scale between 0 and 1. Another possibility is to use standardization. In this case, from each point we subtract the average, so the average will now be around 0, will be 0, and we divide everything by the standard deviation. This means that we obtain a distribution that has an average of 0 and a standard deviation of 1. This is called standardization. So we can use either one. In this case, I'm going to use standardization just to show you how you can do that. We're going to load the data. In this case, this is a tab separated file, so we can specify the delimiter there as a tab. And then we're going to separate this into the epsilon values. We're going to get a matrix with the last column. And the X values, we have a matrix with all the columns up to the left. Now there's a small trick here. These are a lot of details that you don't need to memorize at once, but just keep in mind that there are some of these details when you're working this in practice. If we choose the last column with a -1 there, we obtain a vector that has a dimension of 1, because it's only a single row or a single column, a single array of values. If we want to keep it as a two-dimensional matrix, we need to put that as a list of values. And so in this case, it's actually a column. It's a two-dimensional matrix with a single column. So there are lots of these tricks. The idea here during the lecture is not that you memorize all of them, but just so you remember there are these tricks that you can use, and you can use them then in practice. Now we're going to compute the mean and the standard deviation in the direction of the road. So this is the axis for the computation. This means that the mean will be computed for all the rows in each column, and we get a vector with the means of all the columns, and then the standard deviation, the same thing. Now these two values, the mean and the standard deviation vectors, so these are actually vectors for all the columns. We need to keep them because when we are going to use our model to classify new data, we need to rescale that data too. If we don't, if we simply use the raw values when we are going to try to predict, they will fall completely outside the range we are using here. So remember, whenever you do standardization or normalization, you need to retain those values and apply them consistently to all the data that comes afterwards, even after you train your model and have everything done. So now, to adjust the x values, we simply subtract the means and divide by the standard deviations. These are vectors, this is a matrix, but NumPy does this broadcasting, and we can do this in this way. So basically what we did here was this standardization here, and we keep the means and the standard deviations that we need to apply to all new data. Now we're going to simplify a bit the expression. So we have this inner product of two vectors, which is the vector that gives us the direction of the plane, and the x values, the input x values. And then we add the constant because we may want the plane to be a bit higher or a bit lower when we split the two classes. But we can simplify this into this expression, simply an inner product of two vectors. If we add a new feature which only has a 1, so it's equal on all our data points, it has a 1, and then this W0 gets included into our set of parameters. So this, I'm using this here because you find it commonly in the literature that you have this simplification and then the expression is only a multiplication of two vectors, or if you have a matrix of all the x vectors, you can multiply the vector by the matrix. And this is also useful in practice because when you have to do these calculations, you can do it on a single step by multiplying the vector and the matrix, and you have this inner product done in only one go. So it's useful to simplify this. In any case, typically in practice you're not going to go into this detail because you can use the classes that are already available in the scikit-learn library. So this is not something that you're generally going to use in practice, except in some tutorials, so in order to understand the details. Once you understand the details, you don't have to do this all the time. So this is simply manipulating the matrix. We're going to create a new matrix which is created as a matrix of 1. So this is a large matrix with 1 in each cell. It has the same number of lines as the original one and 1 extra column. And then we're copying the original one to all the first n columns, retaining the value 1 on the last column. So this is basically adding this one value here at the end of the vector of features for each of our points. Now we can measure the error. We have the coefficients. This theta vector will be all the W coefficients there. We have the x values for our data and the y value, the class for each of our cells. So either tumor or normal cells. And now here, this is where this becomes useful because we can compute this for all our data sets simply by doing an inner product between the matrix with all our data, all our points are in rows, and the coefficient vector that has to be a column. So if we do simple algebraic matrix multiplication between these two, we are computing this for all our data sets. So we only need one instruction to do that. In order to do that, we need to put this vector as a column, so we create this coefficients column, which has a number of rows equal to the length of the vector, and one column. This is a two-dimensional matrix with one column. We copy the values there, and then we do the inner product. So this way, we can apply this expression to all our data points. It doesn't matter how many dimensions the matrix has or how many points it has. All we need is this. And then we compute the quadratic error. So these are the predicted values from this equation here. And the epsilon values are the actual class of our points, which can be 0 or 1. However, we need to rescale this a bit because our function will give us negative values in one side, positive on the other. So we do just this trick, twice the value for the class minus 1. If the class is 1, this becomes 2 and the result is 1 at the same. If the class is 0, this is 0 and minus 1 becomes minus 1. So it's basically changing the class between 0 and 1 to minus 1 and 1, but the data is the same. So we're computing the quadratic error between what our function is telling us, and the function says it's positive on one side, negative on the other, and what the class should be. And we are putting the class as negative on one side, positive on the other. And now we minimize that. We can import from this SciPy library a minimization function, and we just tell it to minimize our function here called the quadratic cost. We give it an initial guess for the coefficients, which is just all set at 1, but it will start from that guess and minimize the function by going through the gradient of the function until it finds a minimum. And now we obtain from that the result of the minimization. This is an object that has the number of iterations, the residual error, and so forth, but also has a next attribute that has the final coefficients, the final results obtained after minimization. So these are the best coefficients for our fit, and now we can plot the data, and we see that the result is rather bad. And this is why this is the wrong approach. The reason why this is a bad result is that we are trying to minimize the quadratic error between what our function is predicting, which is positive on one side, negative on the other, and the values for these points, which are minus 1 or plus 1 in our formula. And the problem is that since the values increase on this side, points that are far away are pulling the discriminant towards their end in order to minimize the quadratic error. So since we are using a quadratic function, we are penalizing things that are far away. This makes sense when we are doing regression, because we want the line to be as close as possible to the point, and we want to put a higher penalty on those that are far away from the line. But when we're doing classification, it doesn't matter if this point is far away. As long as it's on the right side, then it's okay. We don't care how far away it is. What matters to us are the points that are close to the line, because this is where the mistakes are more likely to happen. So we should have put the line here, far away from this point, and not try to approximate that. So this is not a good result, because when we are minimizing the quadratic error between what our function is telling us and the value of the class, points that are far away are pulling the discriminant towards their end. So and this gives us a more fundamental idea about the difference between regression and classification. I said on the first lecture that we are doing regression when we are trying to predict a continuous value, and classification when we're trying to predict integer classes or discrete classes. But this seems a bit of an arbitrary distinction. With this example, you can understand better the difference between the two. In regression, we are trying to fit a line as close as possible to all the points. In classification, we are trying to find a way to separate the data in different categories, in different classes. So we don't want the line to be as close as possible to the points. Rather, we want the line to be far away from those points that are close together but belong to different classes. So the objective is rather different when we are doing classification, trying to partition the data, or regression, trying to predict a value. So let's see how we can do this with logistic regression. We're going to assume that there is some function that has some parameters W, and when we input into that function the value of the attributes of some point, the function estimates the probability of a point with those attributes belonging to class 1. For instance, suppose that class 1 is a tumor cell, and if we introduce the values of the gene activation values, the function estimates the probability of that cell belonging to a tumor. So this will be the function we assume exists. We don't know what function that is, but we assume this function exists somewhere. And we want to cut between the two different classes. At that hyperplane, we're going to assume it's a hyperplane, so this is our hypothesis class. We want a straight plane to separate the two classes. We want to cut the data in the plane corresponding to the point where the probability of belonging to class 1 is equal to the probability of belonging to class 0. That is the point where the values indicated it could either be tumor or non-tumor with the same probability. So its probability is 1/2, or the probability of 1 is 1 and we also know that the probability of 1 is 1 minus the probability of belonging to the other, because we only have two classes. So this is a regression because we are trying to approximate this function of the probabilities as well as possible. But what we get in the end is this cutting plane where the probabilities are the same for either class that separates our data into the two classes. So that's why we can use logistic regression as a classifier. So if we assume that our function g gives us the probability of belonging to class 1, and we want our plane to be in the place where the probabilities are equal, we can write it like this. So the logarithm of the probability of belonging to class 1 and the probability of belonging to class 0, which is 1 minus the probability of belonging to class 1, will have to be 0, because the two are the same. This fraction will be 1, and the logarithm of 1 is 0. So this basically is the logarithm of our function divided by 1 minus our function. And it must be 0 where the plane we want is cutting the data. So if we know that the plane that we want to cut the data, if we assume that this line where the probabilities are the same will be this hyperplane in n dimensions, described by this formula, so the vector that is perpendicular to the plane multiplied by the features and then with a constant added, we can see that our function must have this shape. So this only works if the function is 1 over 1 plus e raised to minus the value of that function that defines the plane. So this is basically changing the expression there. And this is the logistic function. So basically, this is this function here. It starts at 0 at minus infinite, then it goes up to 1, and then continues in 1 up to minus infinite as a function of the value that you get there. So basically, we can do this regression by using this logistic function to try to approximate the probability of belonging to some class, and then cutting where, or finding the plane where this is 1/2. That is, the probability of belonging to one class is 1/2, the probability of belonging to the other is 1/2 too. What difference does this make? Note that if we are using a quadratic function for penalizing the distance or for measuring the distance to our line, we are giving increasingly higher penalties to points that are further away. And that's what gives that effect that the line gets pulled to the place where the furthest points are. But if we use a logistic function, then after some distance, it doesn't matter if the points are far away or not, they all count the same. And the same for the other side. What makes the difference are those points that are close to the frontier. And this is more intuitively what we want when we want to choose where to place the frontier. So now we can try to compute the parameters for our function by maximum likelihood. I know this looks a bit scary, but the idea is that you get used to reading these equations. The purpose here is not for you to memorize these equations. I'm not going to ask you to demonstrate these things on the test. But if you want to proceed studying machine learning, you're going to find in textbooks and papers and so on these kind of things describing the method. So you need to learn the language and to get used to reading these equations. So basically, if our function is estimating the probability of a point x belonging to class 1, with the classes being 0, 1, or minus 1 or 1, then what you want. But in this case, we're going to assume the classes are 0 or 1, so we're going to use value 0 for one class, value 1 for the other. We know that the likelihood of our parameters given the data set is the probability of all those classes for all those points. So the probability, the joint probability for everything is simply the product of all the probabilities. And we can write the probabilities in this way. If the point belongs to class 1, then its class, Tn, will be 1, and the probability is given by the value of our function for that point, Gn. If the point belongs to class 0, then the probability will be 1 minus Gn, because that is the probability of belonging to the other class. And then we use this power here because this is 1 when the class is 1 and 0 when the class is 0. So when the class is 0, this term here is irrelevant because it becomes 1, and this shifts the other way. So this is 1 when the class is 0 and 0 when the class is 1. So we can write this because for each class only one of these two will matter. The other one will just become 1 and make no effect on the product. So now we can take the logarithm of the likelihood, we change the product to a sum, we remove all those exponents and get the logarithm and so on, and we have this expression here. So this is basically the logistic loss expression, or the cross entropy between the probabilities, and this is what we want to minimize, to maximize, to get the maximum likelihood. Or alternative, we minimize this logistic loss error, which is basically changing the sign of that one and doing a minimization. So this is the target function that we want to optimize. We want to minimize this error of the product of the label for the class multiplied by the logarithm of the predicted probability plus 1 minus the label of the class multiplied by the logarithm of 1 minus the predicted probability. This works because the class can be 0 or 1, so only one of these two will be used depending on the class of the point. The other one will just be 0. And this function is this logistic function of our plane, the plane that we want to find. So let's see an example how we can do this. We can write the logistic function. This is simply 1 plus e raised to minus x. And then we do 1 over that to get the logistic expression. So this is this function here, where this is the x that we are receiving as input. And then we create the logistic cost function that we want to minimize. We obtain these coefficients. So we have this theta, which is the vector for the coefficients we're trying to evaluate. We put everything into a single column so that we can use the dot operator, the multiplication between the matrices, the inner product, in order to multiply our coefficients by our whole data set. Remember that our data set includes that extra 1 so that we can put all the coefficients into a single vector and do the operation in one go. And now we're going to compute the logarithm of the probabilities for those values here in let me go back. We're going to compute these two terms. So we multiply by the label of the class the logarithm of the probability, and this will be 0 whenever the class is 0, and the logarithm of the probability whenever the class is 1. And then we do the same, but by using the other class, so 1 minus the label of the class, and the logarithm of 1 minus that probability. And this is what we do here. We multiply the class label by the logarithm of the probability, and 1 minus the class label by the logarithm of 1 minus the probability that we compute. So these two variables, log 1 and log 0, are vectors because we are applying this to the whole data set. And now we can add the two of them and we obtain a vector with all the sums. However, this one has zeros wherever this one has does not have a 0, and vice versa, because epsilon can be 0 or 1, and 1 minus epsilon is also 0 or 1 in the other case. So this is the computation of this term here, and we are using the sum to add everything, or in this case the mean, which is this part here, the sum divided by the number of values. This negative sign will actually make everything positive because we are doing the logarithms of the probabilities, and the probabilities are all below 1. So all of this is negative, and then we are minimizing the positive value. So this is the cost. We can use the minimization again. I'm not going to show the code in this case, but we can use that minimize function to minimize this cost instead of the quadratic error cost, and now we get something that's a lot more reasonable. So now we find a dividing line that is not paying too much attention to these points outside, because the logistic function flattens out away from the frontier, and places the frontier between the two classes. Okay, so this was when the two classes are linearly separable. Now we may want to do this when they are not linearly separable. However, we are still using a linear discriminant. So our definition, using that vector and the constant and so on, only allows us to find linear discriminants. So if we try to find these, the same separation between the classes using these two genes, we have something that is not linearly separable, and so our best line is not very good. It still leaves some points misclassified even inside the training set. So what we can do, we can expand the features. We can still use a linear separator to separate points that are not, classes that are not linearly separable. If we do a nonlinear transformation into a higher dimension, and then use that transformation and cut the two classes linearly in that transformed space. So let's see how we can do. We can add a feature here. We're going to create a matrix that is the same as the original one, but has an additional column. We're going to copy the values of the original matrix into all the columns except the last one. And then in the last column, we're going to put a product of the first two values. So we have the activity of one gene, the activity of another gene, and we are creating a third feature that is the product of the two. This is a nonlinear transformation because we are multiplying the two. If we did something that was twice one plus the other or something like that, it would not work because that would still be linear. But we are adding a feature that is a nonlinear computation over the other feature. So now we can do logistic regression in 3D. I'm not going to do it manually, so the first example was merely to show you the details of what we're doing in logistic regression. You're actually, when you're using logistic regression, it's best to use the class that is provided in the scikit-learn library. So you're going to create a logistic regression object. This is a regularization factor. We're going to see it next week better. But if you just put a very high value here, it's the same as not using regularization. So we're going to give it a very high number to switch off regularization. This is the tolerance for when the minimization stops, so for the optimization algorithm. And we're going to do a logistic regression on this expanded data. So now we're going to do a logistic regression in 3 dimensions over the data obtained by using the 2 gene activations plus the product of the 2 gene activations. So basically we get this kind of result. The original points are spread out in a curved surface because we transform them non-linearly. Remember that if we did a linear transformation, we would still be in 3 dimensions, but they would be all on a plane, and we still would not be able to separate them. But if we do a nonlinear transformation, they will go into 3 dimensions as a curved surface, because the transformation is nonlinear. So they are spread out as a ball, more or less, like here. And now if we cut with a straight plane, and we go back to the original space, we can see that this actually projects into a curve, because that's the intersection between the curved surface where our data was mapped, and that straight line, that straight plane that cuts it. Okay? So this is how we can use a linear discriminant in higher dimensions to separate classes that are not linearly separable in their original dimension. And this is something that we're going to see occur in different classifiers. It's still not very good, but we can increase the number of features. For instance, we can add the first one squared and the second one squared. Now we have 5 features. We have this shape here when we project X. Of course, now we are expanding into 5 dimensions, and I cannot do the cartoon of the 5 dimensions because that's a bit harder to visualize. But now when we go back, we have something that is even more curved, and we can go on and increase as much as we want. So what we need to do is always expand in nonlinear transformations of our data, so that when we are projecting our data into the higher dimensional space, it is not in a straight plane, but in something that is curved. And so when we cut it with a straight plane and project it back, we can have these different shapes. And we can do this as much as we want. So now we start seeing that maybe there's a bit of overfitting here, because we are predicting there that those cells would be a tumor cells too, something that fell there, and we are starting to get too much curve in our frontier. So at some point we are probably learning the noise instead of the data, and we are starting to overfit. We'll see how to solve that in the next lecture. So for today, what we saw here in the introduction to classification was this problem of whether or not the classes are linearly separable. This is important because often we are going to use linear discriminants, and we can only separate the classes if they are linearly separable. However, it's important to know that the classes may not be linearly separable in the original dimension, but when we transform non-linearly into higher dimensions, if we transform them non-linear into higher dimensions, then it may become possible to separate them linearly. And this is how we can use linear discriminants to separate classes that in the original data are not linearly separable. We also saw that just doing least mean squares to fit the discriminant does not work, because there is a fundamental difference between regression, in which we're trying to approximate our hypothesis to the data as much as possible, and classification, which has the purpose of trying to partition the space where our data points are into the different classes, into regions corresponding to the different classes. And then we saw logistic regression. Logistic regression is a regression because we're trying to approximate that probability function, so it's a continuous function. However, we can use it as a classifier by splitting the splitting the data at some probability for that. In this case, we use the probability where both classes are equally probable, so 0.5. In the next lecture, we're going to see how we can solve the problem of overfitting in classification, and also more generally with cross-validation. So there are some sections of Bishop's book there if you want to read, and